Another particularly useful approach in inferential statistics is the two-factor analysis of variance, sometimes called a two-way ANOVA. What this allows you to use is two categorical predictor variables in a single quantitative outcome. In this example, we're going to use the built-in dataset warp breaks, which is about yarn breaking during weaving. And the two predictors are the type of wool, which is either A or B, and the level of tension, which is low, medium, or high. The outcome is the number of breaks. It's a quantitative outcome. Let's start by loading the data into the workspace. You now see it's there up on the top right. Let's also make a very quick plot. The easiest one to make here is a box plot. Even though the analysis of variance is based more on means and standard errors, this still gives us an idea that we have one condition that appears to be a lot higher than all the others, and that is wool A at low tension seems to have a lot more breaks than any of the others, although B at medium tension also seems kind of high. What we're going to do is we're going to specify an analysis of variance model with an interaction. That's the beauty of a two-factor model, is that you can see not only how factor A affects the means and factor B affects the means, but the interplay of A and B, specifically to see if it reverses around for one or if the effect of one factor is moderated by the levels of another factor. What I'm going to do is I'm going to save it as an object AOV1 because that allows us to do certain summary statistics on it. The actual function is AOV for analysis of variance. And then I have here breaks. That's our outcome variable because that's what it's called in the data set. And then I have two categorical predictors, wool, which is A or B, and tension, which is low, medium, or high. Plus, I add the interaction term. That's wool colon tension. That's the interaction of the two. Now, another way to specify all three of these, wool plus tension plus wool by tension, is to just put wool asterisk tension, which is what I have in the comment there. That works as well. The one's more explicit, but the other one is shorter. And then the data all comes from warp breaks, so the computer knows where to look. I'm going to highlight those lines and do Command Return to run them. And so you see now in the workspace, I have AOV, my model there loaded. And let's get some summary statistics on it. What we have here is an analysis of variance table. We have three factors. We have the wool factor, we have the tension factor, and then we have the interaction of the two. We have the degrees of freedom, the sum of squares, the mean squared, the F value, that's the actual test statistic. And then there at the end, the last column that says PR and then greater than F, that's the probability value. And we're looking for probabilities that are below 0.5. Now you see that wool is really close all by itself. It has a p-value of 0.58. And so R is marked it with a little dot there at the end. So that's nearly significant. We don't have a huge data set and we have three factors, so that might be something worth looking into. On the other hand, tension seems to make a huge difference. That the high tension, medium, and low tension seem to differ from each other very substantially. We have an F of 8.5. We got a p-value of 0.0069. And then there is also an interaction that is statistically significant at the O2 level. It's not as big as our main effect, but there is an interaction. Now, if you're doing the analysis of variance and you get these interactions or you get these particular results, it can be helpful to look at it in a little more detail. So say, for instance, we look at just model.tables.aov. Let's make that bigger. And what we have here is a table of effects. And that is, we start with an overall effect and we start adding or subtracting a set amount to get to each level. On the other hand, it can be a little easier to look at a table of means. So when I type equals means, what that's going to do is give us the marginals and the cell means. So let's take a look at that. So overall, the grand mean, the number of breaks is 28. Okay, fine. That's across all 6 conditions. The two wools, A had 31 breaks and B had 25.2. Now that appears to be a fair amount, but remember that one's not quite statistically significant. Tension, on the other hand, was a big effect. Low tension, there were 36 breaks across both wools, medium 26 and high 21. That's our very strong, significant finding right there. And then the interaction of the two, what you can see is that for low and high, A had more breaks than B. But interestingly, it flipped around for medium where B had more breaks. That's an interaction effect that often characterizes, for instance, experimental research. Now, if we want to, we can do a post hoc test or after the fact test to see which of these differences are statistically significant among the different conditions. There are actually several choices for post hoc tests. I prefer the Tukey, although in this situation we end up with an awful lot of things to look at. We want to look at not just the absolute difference, but we want to look at the probability. And so what we're looking for here is anything less than 0.5. So BL, that's wool B at low tension, is significantly different from AL. Well, actually, AL is significantly different from everything. That's what we get for this series. Let me highlight all of those. All of those are statistically significant, and AL is different from everything. What's interesting after that is that none of the others are statistically significant. So it's AL versus everything else. By the way, AL means wool A as opposed to wool B, and low tension as opposed to medium or high. And again, you can see it in the chart on the right where the box plot for AL is so much higher than everything else. In any case, those are the basics of a two-factor or two-way analysis of variance, which is a great way of looking at the effect of two categorical variables, both individually and in their interaction on a single quantitative outcome variable.